You said something along the lines that strong acids break apart completely and weak ones do not, and you're correct.
That's it.
Another way you can think about it as well, how I think about it symbolically, is strong substances always have a forward arrow. Weak ones have an equilibrium arrow because they don't go all the way. But any other ways of saying that, Evan?
What if we said it doesn't come to equilibrium?
That works. Yep.
Okay.
Yep. Kim.
So I said like a strong acid always gives away its H+, a weak acid sometimes does and sometimes doesn't.
I'd say that's valid, yeah, because since it's holding onto it, yeah, I think that works.
How effective they break down.
Isn't it?
The difference is due to their composition and how effective they are at breaking down.
Good, yep, because the big thing is all about the breaking down or the breaking apart side of things, right?
So I said a strong acid will like give its H+ ion freely and easily, but a weak one needs more energy to give it.
Perfect, yeah. And it is weird, someone was talking to me more, and I never really thought much about the wording of it, where it kind of feels a little backwards, right? Because weak ones hold onto their hydrogen tighter than strong ones do, right? Which kind of can feel a little bit backwards.
Strong acid of salt base.
Yeah, I just said strong acids fully changed, while weak is only partially. I mean, it's like, it's close, it's close.
I think that you should get 4 smiley faces.
If you have that right, that's 5 bonus points.
Oh, so close.
Okay, so slide that into the middle and I'll pick it up.
So should we add them all from?
Yeah, so add it on if you got the bonus, right?
Oh, do we add them all onto one side?
That'd be great, yeah. Yeah, add it all to one side, save some time.
Okay, it's a little messy, but.
Thanks. Where'd it
Then
go?
pull out your note packet.
I could have gone yeah.
I could have gotten
He's so nice, he's so considerate.
no.
They do have acid in them.
What's up?
Wait, when you still those pumpkins? It is over and I can eat as much garbage as I want, dude. I don't have to be healthy anymore.
Okay, everybody.
Orange. Bad, listen, bad one.
Just by raise a hand, and if you don't know, then just don't raise your hand. How many of you, if I got like approved to do this, feel like you could miss your B6 on Friday and not miss anything important? That sounds horrible.
Yeah, 6 classes.
I don't even know.
It's over. I don't even have it.
Is that SL?
Yeah.
It's well, so B5's
I
a
have a computer class, but we're done with everything.
Friday's a minimal day if you didn't know. So our class periods are only like 30 minutes, which we're already cut on time already.
Yeah.
So I just, and because my B6 and B7 are both smaller, we could combine into one class one day and it wouldn't be too bad. And then we'd have like a full hour.
Yeah.
But obviously, I understand if you have another AP class, but I know sometimes on some minimal days, depending on the class, they may not, it might just be a work day or something like that, right, where it's not a big deal to miss it. So I'll send a message through Canvas to all of you if I get that to work out, where like the school is okay with me doing that, of excusing you from those periods to come here.
Don't ask the school.
Really? We'll just all get excused to do it.
I mean, if your parents want to approve you missing, then of course you could come,
Yeah.
right? Or I guess if you just didn't care about missing and having an absence. But either way, just know that even if we only have 30 minutes together, we will still be doing things on Friday. So if you're not coming on Friday or you have other things and not going to be here, then just make sure you check Canvas for what it is. But if not, we'll figure out what to do.
Why is it a minimal day?
So it's kind of the elementary schools,
So you go by
they're
trimesters and
trying.
Oh, so the teachers can grade. It was something.
Yeah, but I don't quite get why we have to be on their schedule.
Yeah.
I like it. I'll take it. I think it's a.
Maybe it's
See, normally I'd be happy, but I need
Because they do it like when we do it. So like when we have our end of terms, they have a minimal date, but I'm like,
Maybe it's because like parents like pick up their kids at one time and it would be hard to.
yeah, and that's what I'm guessing is just like,
The bus schedule.
It is.
but to
Well,
me
I
it's
mean,
like,
most high schools.
No, that doesn't make sense because my little brother gets to school at like 1:15. Or no.
And elementary schools go on Wednesdays.
yeah, like it's already weird, so, but,
Yeah, I don't know.
Also, I heard that next Friday is also a middle day. It is. Well,
so that's the weird thing is our end of term is the next Friday, but then it's not. And then it
Wait,
will be-
what?
Wait.
This Friday's a minimum day instead of next Friday.
Yes.
Wait, so
Oh.
all the high school teachers don't actually get the grading test ever?
I will take my kid to
Because I mean like.
Not for the actual end of term.
Yes, that's kind of.
Evan,
Can I go to the really
Yeah,
quick?
me too. I already got my scholarship.
so,
oh, I'm gonna be gone that
But I
Friday.
was like, don't feel good.
If I get that.
did you finish everything else?
If you
Okay,
what?
once I get them going on this, I'll come show you something in the lab we need to do. Okay, what we're learning about today, everybody, is a type of substance known as a buffer, okay? In terms of what a buffer looks like, a buffer most of the time looks like this,
Everything was.
Oh, water.
okay? Looks like water, like a lot of things in chemistry do. But what is significant about a buffer, and buffers are actually extremely important when you get to like biochemistry or like environmental themes, is a buffer is a solution that does a very good job at regulating pH. Now, to give you an example, water, actual water, is not a good buffer, okay? If you add a single drop of hydrochloric acid to water, the pH is going to plummet. It's going to drop like crazy. Or vice versa, if you add a drop of base to water, it's going to spike. But a buffer, you can add strong acid or strong base and the pH doesn't change. Okay? So before we get into that, let's just review really quick. So don't say anything out loud. The first smiley face, think in your head. Okay, what is pH? So think in your head for a second. What does pH measure? Somebody's gonna have loud heads. Okay, turn to your table, buddy, and remind them what is pH. Go.
Or, yeah, acidity of,
I started grading so I I gotta say, eating a sucker with a mask is the most awkward thing ever.
Think about that.
Yeah, it's so awkward.
Yeah.
That's why I find it.
Okay, raise a hand for smiley face. What is pH? Zach?
It measures the concentration of acid and base in the solution.
Really close. Out of smiley face because it's good, but let's get more specific. What is pH really just measuring, Kimberly?
The concentration of OH minus and H plus in a solution.
Perfect. Right? Which is acids and bases, but that's the amount. So it measures when we calculate it. Okay, next time we'll use our pH probe. So what a pH probe does is you stick it in a solution and it can detect.
Wait, does it change colors, those ones?
We will be, yeah, next time we'll use some of the common ones. So we also have some like electronic ones that just give you a number.
But the other ones are so much more fun.
But the other ones are more.
Wait, is that like in a pool?
Yes.
Yes.
Yeah, so whenever you see the lifeguards go over and scoop up some water and then they go like
Yeah.
this.
Yeah.
Yeah, they're checking the pH levels.
Yeah, but that's chlorine.
Well, maybe that's the.
That's one. They check for a variety of things.
It's also like the explode.
Back to the video. Okay, so with a buffer here, everybody. Okay, a buffer's job is to not change in pH when you add something to it. Okay, so if I pour in an acid to a solution, I'm adding more of this, which is why the pH goes down. If I pour in a base, I'm adding this, so the pH goes up. So the analogy I'd come up with buffers is buffers work, okay, if we could zoom, this isn't a buffer, but just pretend, if we could zoom into a buffer at the molecular level, okay, a buffer contains things in there that can battle anything that is added. Now what's significant is you need something that can battle this, and you also need something that can battle this.
You stick up the hydrogen.
Because if you use this up as it's dropped in, the pH won't change, right? Or vice versa, if I use this up as it's dropped in, the pH won't change.
Is it like an equilibrium?
Kind of. Yes, there is an equilibrium side to buffers for sure. So let's look at some equations at the molecular level to kind of understand what will make a good buffer. Okay, so if I take a strong base, so that's what this is. So this is sodium hydroxide, everybody. Okay, this is hydrochloric acid, a strong acid. Okay, we're gonna pour them together. Everybody ready? 1, 2, 3.
Boom. Now it's water.
Oh, it didn't do anything.
It's amazing.
When you, it didn't like blow up or anything.
Wait,
Yeah, I was waiting for the baking soda.
Okay, so let's dive deeper to see what happens, since to our eyes nothing seems to happen. Okay, so let's go to what's known as the complete ionic equation, which looks at the things as they truly exist. So what do we, when something has a strong base, what does that mean?
It's a high pH,
It has a high pH. What else?
high concentration of
Good. And what else?
it is a strong base.
What do strong bases do?
It won't
They're basic.
big
Yeah, basic.
This
Sorry, say that again.
is
say it again.
really that,
Oh.
right? If we can
Oh.
zoom in to our beaker, everybody, and see what's floating around, I'm not gonna see this, I'm gonna see it separate because it's strong. Okay? Same thing, this breaks apart. Because it's a strong acid.
So that becomes salt and water.
Whoa.
Wait, so if I drank that, would it just taste like salt water?
I dare you to drink it.
It should, right?
Whoa! The fate. The fate. She would die for this.
Okay, just kidding, I have to tell you the truth, it's actually just water.
Oh my god.
Okay, that-
You made the face.
I know, I just had to trick you. But technically, if you have these two things and you mix them together, what are you gonna make? Salt water. Salt water. Wow, now why would you not want to drink it?
Because salt water is bad.
Salt water is still bad.
Yes, right? If you had any excess of one or the other,
Oh, true.
Okay.
that would be so
But
fun.
doesn't your blood have buffers in it, so could it like survive?
Yeah, but why would you
Does
want
it?
Yeah. That's
Yeah, why?
You go over like, I'm done.
Yeah, the process of it corroding down your throat is what I'm worried about, so.
I don't know. I mean, have you seen those like smokers that have holes right there?
There you go.
Like the fashion statement.
It is a fashion statement.
It's absurd.
Okay. Focus back up here, buddy. I just realized we had a problem we didn't solve last time. So
Yeah.
access we gotta make up. Okay, we'll come back to that here in a second. Okay, so this is the present of how they actually look if we can see them. Now at this point we can kind of ignore the things that didn't change our spectator ions. Right, so we can take sodium and chlorine away.
Get that break out.
And then the net ionic equation shows the main things that are happening. So what's interesting is regardless of what acid or base you use, if it's strong or which strong ones I should say, the net ionic equation is always the same. So strong reactions always end up with a net ionic equation of making water. Now once again, the pH doesn't mean it'll be right at 7 if you don't do your ratios perfectly, right? Got it.
Is it supposed to be OH plus?
No.
Okay.
Oh, jeez.
Thank you.
Okay, I wrote OH minus.
Hopefully you wrote what I
I
wrote.
totally wrote 8 plus.
Okay, let's look now. So this is strong to strong. Let's look at a strong to weak and see the difference. Now, what did we say the difference is between a strong and a weak?
If they break apart all the
Concentration.
way.
Or
Good.
yes.
So weak acids,
I'm trying, man.
You know that song?
No, I don't.
Oh, bad.
do not break apart completely. And in terms of the amount, majority of weak acids have a less than 5% ionization. That means 95% or more stay together. Now, side note, you may have seen this a lot in your book, HA is just the generic way to talk about any weak acid.
Oh, I was so confused.
Yeah, so it's like they don't want to pick a specific one because there's so
Yeah, I
many
saw
of
that
them.
question on the thing.
So,
Like, what element could that be?
Oh, we got you.
I
So when we come to the complete, everybody, weak acids stay together. Yes, some of it is breaking apart, but in comparison to how much is staying together, it's so little. So we don't write it broken apart like we did for the strong. Now NaOH is strong.
That's
Breaks
bad.
apart.
Strong
It was very start.
Dude, but every single time she says it, that's what I think of. I'm sorry, okay?
It's okay,
'Cause
me too, too.
That's good marketing.
It
They
is good
really got in
marketing,
your
it's
head
true.
just by that single word.
Strong.
Strong Volkswagen.
No, it's complete ionization. Oh, that's right.
Okay, so make a note to yourself that this state is this because it's a weak acid. It doesn't break apart all the way. So in this case, our net looks a little different. Now we don't have as many spectators. We do still get water in the end, but it's not the same as it was before.
Okay, and the arrows need to go both ways.
Yes, because it's weak,
It's the same like you can't.
right, that's why the process isn't going all the way.
Whenever she says it's strong, I'm like strong.
I hate Volkswagen, I'm
Yeah.
sorry.
Okay, now, for the battling species,
Your marketing campaign is so good.
okay, do I need to help us out and move over here?
No, we're good.
You
You
sure?
got this, yeah.
100%.
I believe in us.
Okay,
No,
I don't
Volkswagen.
right now, but prove me wrong. Okay, so what we need with a buffer solution is we need those two things to battle out whatever is added. Okay? Yeah, Evan.
On the last question, why wouldn't we just like, or could we just infer that the A means sodium? Cause like that's how the equation would work. 'Cause it's,
No, because it probably, it wouldn't be, the A wouldn't be sodium because it's gonna be a negative thing because it's with H.
It would have
That's
been
the easiest
CL.
way of putting it.
Sodium
Oh,
comes with the
Would it be
NaOH.
CL?
It would have been CL, but yes, I see what
But,
you're
and then
saying.
the reason why it's not CL, I see what you're getting at now, is if it was HCl, is that a strong, that's a strong acid. So that's the whole thing is with weak ones, they don't cancel out as many spectators as with the strong ones. So, does that make sense?
Yeah.
So this equation just doesn't make sense, or why?
No,
It's
yeah.
kind of a similar
Why would
people
the
who
CL
wrote it know they're
minus
talking
one
about.
and the
Yeah, it will hopefully make more sense when we start bringing in actual weak acids. It's a little like, it's helpful to use the HA to speak generically, but it does sometimes make it confusing because then you're like, wait, where's that A going?
Where's the
And
CL coming from?
where's the CL coming from? So, okay.
Oh yeah, I said Na, I meant CL.
I think,
yeah, my bad.
So this is the equation. I'm just gonna write it for now, and then we'll get familiar with it here in a second. This is known as the Henderson-Hasselbalch Equation.
Hasselbalch?
I love it.
Call me Henderson-Hasselbalch.
Henderson-Hasselbalch.
Save it.
Okay. It is on your formula sheet, by the way, so you don't need to memorize it. We're just gonna learn how to use it. But this is the equation for buffers. It helps us understand this relationship of having two things and then what pH you would need. Okay? So we're gonna, I'm gonna rearrange something just really quick in our notes and then we'll come back.
Is that how pH is always written, or pH is small p?
Yes, because what pH stands for is it's the power of the hydrogen, because that's what it's measuring is the amount of H plus.
That's kind of cool, actually.
So, okay, turn to page, we're rearranging really quick because I found it made more sense this way. Turn to page 7 where it says the Henderson-Hasselbalch equation. So this problem right here, everybody. Everyone found it? Okay, I'm gonna do the first one with you and then you'll try the second one for a smiley face. Okay? So this one says, what is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate? And then it tells us the Ka value is 1.4 times 10 to the negative 4. So what we're going to do is pKa. Now reminder, pKa means you're taking the negative log of the Ka. So pKa is the negative log of the Ka, and the Kas will always be given. That's like a known book value, okay? Plus the log. Now really this is the part where most people get mixed up is the fraction, okay? The acid value should always go on the bottom. So the amount of lactic acid was 0.12. And then the other one, which is the common ion, goes on the top.
Wait, so why does it use A? There, like the A on top. It's
So,
just, like,
so sodium lactate is NaC3H5O3.
I love how you just know that. That
Sorry.
gives me great happiness.
And so, no wait, I already took the HF, sorry, H5 was right. So what it's saying is that when this loses its H, we're left with C3H5O3. So that's where the C3H5O3, so this is like H, if you look at this as HA, that's why this is classified as A.
Oh.
Does that make sense?
Yes, thank you.
So, no, good clarification.
Because I'm like, there's an A, I'm like, are those the same A's or?
Gotcha. Yeah, so it's just saying it's the thing that is attached to the acid, but without the H anymore. Okay? All right, let's practice typing this in to make sure we can all type it in correctly with your calculator. If you type it in correctly, you should get, I think, 3.8. So everyone try that for me really quick, just to make sure we don't have any calculator issues with typing in logs.
Is there a bonus calculator just sitting around? A bonus calculator.
I think you should get extra points if you plug this in correctly, you know what I'm saying?
Is
Oh,
it
I
back in
saw
the-
that. I have an extra calculator. Never
Oh, oh, really? Oh, thank you, she's got me one.
Wait, 3.77.
Yeah.
Use that one.
I think I did. Thank you, though.
These ones you just have to type in the number and then hit log instead of log then the number. I was out there.
I don't know what you
Wait, so is the 3.8 the pH? What's the 3.8?
That's the final answer. So if you typed it
So
in
the
right,
pH equals 3.8.
yeah. So practice, just so we can make sure there aren't any calculator issues.
No.
Yeah, I did some.
It's very difficult.
If you didn't get that number, let me or someone know so we can just make sure it's good. It's not a hard problem, but I hate for people to get something wrong just because you don't type it in the way it should be typed in.
No, that doesn't make sense. Yeah, you got it.
You write 1.4 times 10 to the 4.
Okay, once you get 3.8, actually, let's have you try practice 8.9, the problem right below for a smiley face.
What?
Okay, so try, once you get this, so you know you did this one right, try the problem right below it for a smiley face.
Ints? What does ints do?
It inserts things, so like,
Oh, so I could have just deleted it.
Well,
so if I click that,
Yeah.
changes it, I do that.
yes, so try the one right below it.
Oh, we're doing the next one now?
Yes.
Wait, how do we
Oh,
know
yeah,
what's
I-
A and what's B? Oh,
What?
Wait,
Wait, what?
so we're doing this as a part.
because it doesn't make any sense.
It's individual. Okay.
Look
at these. So,
Which one is it? Which one is it?
Alright.
Yeah, everyone else
Same answer that I
I'm no third.
Is that how you, is that the equation?
yes, that is.
Concentration of.
I gotta write the plus, but I knew there was a plus there. So I put it right here.
Ooh.
Afterwards, it's like,
I just think I'll get
So-
that. I don't know if that's right, so maybe. Try that one.
Wait, how do we know which one's the first?
So, it'll have the H in it, cause like up in this one is sodium lactate, so this one has sodium in it, and then that one has.
No, you got it.
Okay.
Yeah.
So I did it.
But I don't know if I did it right.
0.123.
Me and Landon got the same thing. So,
You,
did you guys get it?
here.
3.744.
Wait, 3.75.
Yes, but I'm not sure that it's the answer.
Yeah, I know, I'm not,
I'm guessing.
like to the point 0.001 on top, or does that?
Oh, yeah.
Because the acid always goes on the bottom.
Just.
Well, it says
the
above
addition
that.
of-
It says above
Oh,
that, so then
my
it
bad.
should be the same order.
No.
That is true, they are the same thing.
Right.
Oh, you gotta be kidding me.
Yeah, so I'm
This is
guessing.
so
I
sad.
think that was probably the same.
Okay, sorry everybody, just getting them set up for our lab next time. If you got 3.74, you can have
That's
some
my-
questions on how to use Henderson-Hasselbalch. It's pretty straightforward, but yeah, that's right. Kimberly.
How do you know that one's an acid? Just by looking at it.
Often the H is in the front, and the second one it's a little deceiving because it's not. The simplest way is whichever one has the Ka is the acid,
Well, because in his calculus.
because
he
the other
put
one,
the
like
extra
only
O
acids
beside
have Ka values.
No,
So that's how I would go off of, and you can't
Opposite
tell
of
by
that,
the
you could
formula.
go
Right.
O, O,
So-
Hoping that it's
Well, I looked at the other problem and the acid was a higher.
Okay, let's backtrack now to where we were before.
You're supposed to put the point zero
Okay, so with this idea of a buffer, everybody, okay? Once again, what we need is we need something that can battle strong acid and something that can battle strong base at the same time. Now, the thing is buffers are good at regulating pH, but they're good at regulating a very specific pH. For example, our blood is a buffer that regulates between 7.35 and 7.45. It's a very good buffer for that range,
I'm very curious how someone figures that out.
okay?
Just don't think about that.
But in another case, you may need a buffer that regulates at a lower pH.
Can I please get Zara Brunson to check out?
Yes. For a second, I almost totally had the wrong room. I was like, I don't know who that is. Oh wait, that's Mina. Okay, so with this idea of a buffer, the way you pick a good buffer is by going off the pKa of the acid. Okay, so for example, in our lab, this is the lab challenge next time. Okay, I'm gonna put you in lab groups and I'm gonna give your group a pH. And then you're gonna go into the lab and make me a buffer of the pH.
That sounds pretty awesome. We should be able to
And your
choose our
grade
lab
is the
group next
pH meter when I stick it in.
Can we choose our lab partners?
time. Yeah, can we choose lab partners?
Yeah, because we've done random lab groups last time, so I'll let you pick lab groups this time.
How many people are in the group?
I'll have to calculate my numbers.
I think.
I think I did 4 last year.
We should
I think I did 4 to a group. So anyways, the first thing to pick a good buffer is to pick which acid you're going to use to make it with, and that's based off its pKa. So the goal is to have a pKa that is as close to the pH as you want. Now, what that tells us is an interesting relationship, okay? So if the pH of your buffer is less than the pKa of your acid that you're using, think this through just on the pH scale. Okay, so a pH scale is 7. Where do acids fall?
beneath that.
Lower.
Good, so acids are here, bases
You know
are
that
here.
water has a heart too, so
Okay, now in terms of a buffer, the acid is always whatever we deem as HA. The base is always the A minus. Okay, so it's always a conjugate pair to make your buffer. So if the pH is less than the pKa, what do you have more of? Do you have more acid or do you have more base?
More acid.
Yeah, does that make sense? Because it's lower than on the scale. So this would tell us that your buffer has more HA than it does A minus, because the pH is lower than what it would be already. Okay, so as you're thinking about these problems and things, once again, I encourage you not to memorize ups and downs, but just think logically about what makes sense. And with a buffer, or with this scale, lower pH must mean you have more acid than you do base. Now the goal of a buffer is to have these as close to each other as they possibly can, because that was what will help it battle, and that's what we'll look at here in a second. Okay, so we'll see more of this next time, but indicators are things that you can add to a solution to help identify pH. It's like a visual way of detecting it. pH meters are like the technical way because they'll give you an actual number, but indicators can give you a color that show it. The interesting thing is there is like, I don't even know how many indicators in the world, and they're just a rainbow of colors for whatever you want. But you just kind of pick it depending on what you're trying to see. So once again, we'll get more familiar with indicators as we work with them next time. That's kind of what they are. So, okay, in making a buffer, so here's our steps that we're going to follow next time to make in our actual buffer. Once again, we need species that can battle H plus and OH minus. But then there's another stipulation that we need as well. Is those species, so I'm going to lower this down so I can write a few notes on it, can't battle each other. Okay? So we need something that can battle H plus because that's what happens when you add strong acid. Okay? You need something that can battle OH because that's what's going to happen. What's the problem if they battle each other though? What do they make?
Water.
Water. And
Water's not a good buffer. It's all coming together, dude.
Okay,
I understand.
so that's the trick is you need things that can't battle each other to make it work. So here are two methods in a lab that you can use to make a buffer. Okay, first step in both cases, you always need a weak acid or base. We're going to go on the weak acid side, just because that's how we're used to using the Henderson-Hasselbalch equation. But there is actually, when you do your reading tonight, there is a base version of the Henderson-Hasselbalch equation. It's very similar, but it's just POH equals the PKB plus the log. You don't need to write this down, but just so it's just like the same equation, but in base terms instead of acid terms. But the acid one is really the one that we'll always use.
So it's literally the same exact equation. It says different.
Well, that
Yeah,
makes
pretty
sense.
much. Because the problem would just give you these different things.
Yeah.
So, yeah.
Okay.
Okay, so the first thing is we're going to start with a weak acid. Okay? So here's our actual weak acid. So we're not looking at HA anymore. So hopefully this will clear things up. Okay? Now, if I just have a beaker of weak acid, what do weak acids do?
They did say.
Break a little bit.
They break a little bit. So this is floating around in my beaker. But then some of it breaks apart. All right. So a weak acid as is, that's what's floating around. So think of this is what's floating around in my beaker. If I were to add some strong base to this substance, this right here could battle
Oh, I
Okay.
see.
it. So this can battle any OH that gets added, because the H
But the other
can bond with the OH and
That's
make
kinda cool,
water.
dude.
Okay, this can battle H plus.
Wait, but does that mean that the buffer has to battle itself?
But we don't want it to battle itself per se, right?
But it creates the H plus. There.
Say that one more time.
So the C2H3O2 battles the H plus, but there's already another H plus floating.
Oh, so this is, maybe I should say battles any added H plus?
Okay.
You are right, it does, because that's why it's in equilibrium, right? But I guess what we meant, they don't battle each other, is this won't ever react with that together. Like these two things won't cancel each other out.
Oh, okay, got it.
Does that make sense? I see what you're saying though, because there is an H plus already there. Because once again, the whole idea of a buffer is to keep the pH from changing. If I don't want the pH to change, I need to cancel out what's being poured in. So this can cancel out OH that gets poured in. This one can cancel out the H plus that gets added in. Now, why though then is a weak acid by itself not a good buffer that has both of those things?
But it doesn't do that very often, right? It doesn't break apart often. So there's not that many.
There's our problem.
Yeah.
How much of this do we have in an actual weak acid?
Like, not a lot.
Like none. So what we do to make a buffer is we add something that can bring this with it, such as a common salt. What do salts do in water? They dissolve, break apart, and so when you add sodium acetate, you're adding more of that A.
I have a question.
Yes.
Could you put enough acid in, like, destroy the buffer's effect?
Yes. So we have what's known as the buffer capacity, which you can break. So that's another thing we'll do in our lab is we'll make a buffer, test a buffer, and then break your buffer.
See.
Oh, that's sad.
The joy in your eyes.
No, it's cool. It's really cool to see it, like, yeah, I don't know how to describe it, but it's cool to see it break. Evan.
Wait, so when we do our lab, is it all just gonna be like clear water? Or not water, but like,
Pretty much.
okay.
Yeah. Besides, we will add indicators so you can see the
Okay.
change.
He's gonna, like,
I thought
swim and like just make
we're
all
just-
the cups
wow.
water without telling them.
So, yeah, so that's what's cool with the breaking side is the color change that happens when you
Oh,
break.
okay.
Wait, so is this lab next time?
That's the plan.
So if we can get out of our B6 class.
Well, that's where I'm trying to decide if we can't, then we'll start it next time and then probably finish it the time after. But, yeah. So, okay, questions so far? And understand this concept of what a buffer is at the molecular level. Okay, another way we can make it, so that's one way to make a buffer is by adding a weak substance with a salt. Another way is to add a small amount of strong with the weak. So for example, we're going to add some sodium hydroxide with our weak acid. So we have HC2H3O2 again. Okay. This time I'm going to add some sodium hydroxide, which I'm just going to take out the sodium because it's a spectator, kind of like up there with the sodium acetate. Okay, so the OH is coming from the strong base. When an acid and base react, the acid donates its hydrogen, so it will make water, and C3H3O2 minus.
C3?
No,
Keto.
C2. Thank you. Okay, for two smiley faces, circle your battling species in the second equation. It's like I circle them in the front one. What are the two battling species in the second?
Oh.
Just circle
Wait,
them
so
around.
that's not equilibrium, right? That's just like falling to the other side? Okay.
It is reversible, I guess, but it's not like a balanced state.
That'd be good.
Okay, you circle.
Okay.
Turn it off now.
When he's hesitating so much, I doubt myself so hard.
Then everyone's like, should I say wait?
It's
Alright, let's see.
Okay, if you circle this, how's smiley face? So this can be used to battle OH, which it already kind of did. But if you add more of it, right, it can keep the pH regulated, and this is your other one.
And that was H plus.
Say that again. Yes, so this would battle any H plus, that's it.
Okay.
Now, why is it significant, or why is it important that we're only adding to make our buffer? Why do we only want to add a small amount of the strong one?
Because if you had too much, then we'll just like overpower it.
Yeah. If I had too much of this, all of this will go away. I don't want all of this to go away. I just want to make some of it into this. So for example's sake, what you could say is, let's say I had 10 molecules of this guy. Okay? A good choice would be to add 5 of this one. Why?
Then it'll make fun of the.
Yeah, because then in the end, it will make 5 of this, and how much will I have left over still? Yeah. And so that's a good buffer, because you have both of them present. If you add too much, you break your buffer before it's made. Yeah, Zach?
So if you have like a very acidic thing, would you want to add more of the OH so it makes more of that? Balance out more of the.
Good, yep. Yeah, depending on if that's the direction you want it to go. So, okay, any other questions right now for buffers? Yeah, Evan.
Wait, so theoretically you can like break a buffer either way?
Yes.
Okay.
Yes. So what we have, let me go to the next one that kind of goes along with that and what Taylor said, is the buffer capacity. So buffer capacity refers to pretty much how long, in a sense, a buffer can last. And it's all about just how much concentration you use, right? If I have a lot of concentration, then the buffer is going to last a long time. But once that concentration runs out, right, if this is gone and you add more acid, it's not a buffer anymore because it can't get it away. That's an interesting question I never thought of before, is how does our, like, the buffer capacity of our blood?
So you're telling me as if like you drink or you ate so many lemons that you just like died?
You know, like,
That's kind of concerning.
I
need
think
to
that
wash
goes
my
with
lemons.
anything.
Wait,
You
would
could
that
die
mean
from
that
eating
there'd
a lot
be
of
like,
anything.
this sounds stupid, but like a little bit of lemon stuff in your blood?
you're gonna inject yourself with lemon?
Well,
Oh,
like,
don't say that, don't say that.
but like if it broke the buffer, then would there just be like some of the like
Just the lemon juice
particles?
floating
Water in your blood.
So-
I guess it would just be the acid.
Yeah, so there's,
Okay.
what is the medical term of when you get to acidic?
Is it like
No, that's.
I don't know, but there, yeah, there's like, it's like, yeah, really bad if your blood gets like below that 3.5, but
Lemon eating
I
contest.
don't know, I'll have to go.
Gross.
Yeah,
Don't you
My-
die if you inject your
Wait,
blood?
I
It's
feel
just
like maybe
water.
the way the blood works is it assumes that you'll die by eating whatever you're eating before your blood pH gets messed up. You know? So
Maybe
whatever
that's
you're
like
eating
that.
will kill you before your blood pH matters.
If you eat it fast, you will, right?
You know, if you eat like so many bananas, you die from radiation.
Well, you
Yeah,
die a lot
your
sooner
stomach
from
would burn so
exploding.
far.
Well, it's
Yeah.
literally like 100,000 pounds of bananas, but
It's like you'll die from like.
You'll die from eating the bananas before you actually die.
you die from the radiation, but
You can heal
yeah, or like
cancer.
apple seeds or whatever.
Or like the arsenic.
Stop dying.
Okay, here is your walkthrough of maybe how you want to solve your lab problem next time.
Oh, it's cheating.
Somebody video this. Oh wait.
So,
It is big, big.
my goal, okay, is I want to make a buffer with a pH of 4.55. Okay, that's the buffer I want to make. The supplies that are available to you next time are, I have these 3 acids that you can pick from.
citric
and then
acid.
some corresponding salts.
She's just gonna have some oranges.
Yeah, we're gonna have to
You're gonna
squeeze them.
skeet your own
Yo,
acid
dude,
out.
I love it. We should do that.
No.
Would we solve it by like trial and error, or is there like a way?
There's a way, yeah.
Wait,
Okay.
This
You'll
is
be
the
there
way.
a long time if you
You
try.
should actually just bring oranges there so we can eat acids while
Or just bring
while
lemonade.
messing with
So we
acids.
can
While
drink
we're working with
And then we
acids.
We should
Okay.
drink acid.
So, we're gonna use the Henderson-Hasselbalch equation here,
Oh wait, I'm in it.
but in a little bit rearranged order from the first two columns we did.
Yeah, what is pKa?
What is that?
pKa is just taking the negative log of the Ka.
Oh, cause K.
So then what is the Ka?
Yeah, that doesn't.
Okay, so let's back up. So let's remember, what's Ka? What does any capital K stand for?
Oh,
Right.
it's the concentration of the
Of the
of
mol.
the thing.
The
Oh,
the
no,
molar.
what's the word we're looking for? No one said it yet.
Constant?
Constant for what?
For equilibrium.
There it is.
Ah, it's
Equilibrium. So it's the
constant.
equilibrium constant. So this helps us understand how much of it is actually breaking down,
Mm,
right? Because like none of them break down very much, but this one breaks down a lot more than these ones do.
okay, and then the P just stands for negative log.
Yeah. So P's like a function kind of just say take the negative log of that.
Well, why do you do that? Like, what's the purpose of making
Gentlemen?
that?
So let's do that. Everyone, someone help me out here. Someone plug this one in. What's the negative log of this number? Check that. Someone do the second one and someone do the third.
Oh, I got this. I got the third one. I got the second one. I got this.
He's all yeah.
Just casual.
Negative log.
Shout it out when you get it, someone.
Okay, 4.7447.
Is that the top one?
Yes.
4.74474327.
Yep.
Oh
What's
my.
the next one?
3.13.
1, 3.
What's going on?
Okay.
You want to calculator?
Oh.
Hey, hey,
You like 6?
6.34.
35
Yep.
Okay.
Oh, I forgot.
So what taking the pKa does is it helps us understand what the pH is going to be of it. Which for us, this tells us if I want to make a buffer of a 4.55, this is going to be my best choice because it's the closest to it.
Wait, what was that?
Science.
What was that thing about the exponent and you could guess the pH? Was that like,
Yeah, so you can estimate a log by just looking at the power.
oh yeah?
So like this one is gonna be between 3 to 4, this is gonna be between 4 to 5,
Oh.
Okay.
that one's gonna be between 6 and 7. So technically even without plugging it in, you could tell that first one's gonna be your best choice.
You can guess the pKa of it?
Yes.
Okay.
Pretty much that was just for estimating a log of a number without a calculator.
For like multiple choice.
Yes, yeah, so yeah, that's actually a good point because they could easily bring up pKa questions on
really?
multiple choice.
Oh, that's good to know because I would just be sitting there
Yeah, 'cause I taught
like,
you.
Oh, you're good. She just taught it.
oh. Calculators, man.
All you do, Taylor, is just look at the
Well,
numbers.
yeah, you
got
just
it.
do this.
One of those.
What?
But yes, it is part, they expect you to know how to do that mathematically without a calculator, so. Okay.
What's my name?
Have a heart attack.
What do you mean?
There's my name right there.
Congrats.
Well, I saw a name, like,
Okay, so now, the difference is with our Henderson-Hasselbalch is I know the pH I want, 4.55. Okay.
Oh.
We know the pKa now, because we picked our acid of choice,
Ooh.
okay? What we're trying to find,
is what's inside the log.
kinda, we actually will know one of them because you can't have two variables, right? Okay, once again, these are your acids and they are in, so in the lab, these are already made to a 0.1 concentration. So HA is 0.1 because that's the concentration of acid we're using. We need to find how much salt to add to get our number.
So we should.
This is gonna be fun.
Wait, should we write like molarity? Because what's the units gonna be?
For, in the end, it will be molarity, yeah.
Okay.
Yeah, so if you wanted to keep the molarity unit, it would, but, or just know it's gonna end in molarity too.
Okay.
Okay, so now we have to solve this mathematical thing. We have 2 minutes, can we do that?
Oh, let's go. Speed, like in the queen.
Okay, so my first step is I would minus this over. That's what I would do,
Okay,
so
equals
1/9.
They get rid of
log.
log again. Oh, don't be an exponent or something like that.
Wait, how do we get like rid of log again? Don't we just do
Yeah,
like?
don't you like put the 10 underneath?
Yeah, so to get rid of log, you're gonna do 10
So
to
it'd be
the
like-
negative.
You
So
like
it'd be
put
10
like,
to the power.
yeah, so the way I write it, so I just write like a 10 there.
That would give you x over 0.1.
All of
Everyone good so far with your math? Steps?
I literally, I think it's.
Yeah, I'm good. My math grade
Yeah.
is not elevated.
You're good, so to get rid of a log, you just take 10 to the power of that number,
So then.
and in a sense, it just cancels out the log.
Cool.
So that's why the log is a log.
Base 10.
Yeah, because if you take 10 to the log of something, it just,
Oh, wait, I'm an idiot.
I will try and remember that.
I agree.
then
Yes.
times that through,
Sick.
and I got, so after I did this to that, I'm gonna write it up over here.
0.065.
Yeah, I got points. I'm gonna just take it one step back just to show. Okay, so after plugging that in, I get 0.645, and then move the
What are
0.1
six?
over, so we get 0.0645. There.
Oh, cause you got, okay.
Questions on any of the math steps? Okay, now, food for thought for next time.
I love food.
Is that how do you take this into the lab and actually make something?
That's a good question.
That is a question.
Okay.
Definitely.
Think about that and then we'll talk about it. Okay? Okay, homework is to finish up.
Take it, Benji, good one to the front office, please.
I mean, to do this one, this is about Henderson-Hasselbalch Equation. And then summary.
Did we ever do the question for last class?
No, so you still can't do worksheet 8.2 yet. We'll figure out how we're gonna get that. I just wanna roll with buffers and I didn't wanna interrupt it. Lose our train of thought. So the one I assigned last time where you did like 2 problems, you still can't make it. That's the hope of the lab. The lab will then bring to light all these numbers.